Welcome to The Explainer. Today we're diving into a huge idea in software, object-oriented programming, or OOP for short. We're going to look at the massive shift that took developers from just writing code line by line to building these powerful, reusable components. Think of them like digital Legos, modeled on the world around us.
So here's the plan. We'll start with why we even need objects in the first place, then we'll break down what an object actually is, see the rules that govern them, and then, we'll get our hands dirty with some actual C++ code. Let's do it.
All right, so let's set the stage. Before OOP, programming was, well, it was mostly just a long list of instructions for the computer to follow. And that worked for a while. But as our software got more and more complex, it created this massive headache of repetition and, frankly, chaos. And this question right here, this was the breaking point. Managing big programs was becoming a nightmare. I mean, imagine you build a huge, complex app for a client. Then the next client comes along and wants something almost identical, but just a little different. Do you really have to rebuild the whole thing? It just wasn't working anymore.
This picture really gets to the heart of the problem. You code a user interface for an app. A form, some text boxes, a submit button. Awesome. But then project number 2 comes along, and even if it's 90% the same, you're right back at the beginning, coding those exact same UI elements from scratch. So inefficient.
And that frustration led to the big promise of OOP, reusability. The game-changing question became, what if? What if you could build that button just once? Create a perfect, universal blueprint for a button that you could just grab and reuse in any project forever. That idea, it changed everything. So, to make this whole reusability thing work, developers had this brilliant idea. Let's model our software components after things in the real world. Seriously, anything. A car, a person, a bank account, they can all be thought of as objects. And every single one of these objects has 2 sides to it. First, it has properties. That's the data that describes what the object is. So for a person, that's their name, their height, their eye color. And then it has behaviors. Those are the actions that it can do. A person can walk or talk or think. Now in C++, we have specific words for all this. That blueprint, the general idea of a person, that's called a class. But a specific person created from that blueprint, you, me, anyone, that's an object. The properties, like name, become member data, and the behaviors, like walk, become member functions, which we also call methods. Okay, what's really important to get is that OOP isn't just a free-for-all, build whatever you want kind of thing. To keep it all organized and powerful, it's actually built on 3 fundamental principles.
And here they are. These are the 3 pillars of OOP. You've got encapsulation, inheritance, and polymorphism. These 3 rules together are really the foundation of any good object-oriented design, no matter what programming language you're using.
So, in a nutshell, encapsulation is all about protection. Inheritance is about building new things from old things, and polymorphism is about flexibility. For this explainer, we're going to zero in on the first, and you could argue, the most important one, encapsulation. The whole idea behind encapsulation is actually pretty simple, but it's so powerful. It says, your object's data is important, so you protect it. You hide it away inside this capsule of code. And the only way anyone can get to that data is by going through a specific set of methods that you, the creator, provide. This quote is basically the mantra of encapsulation. You absolutely do not let the outside world just reach in and start messing with your data directly. That would be total chaos. Instead, you create specific functions, like setBalance or getName, to manage it safely. You are in complete control of your object.
All right, enough theory. Let's see what this actually looks like in real C++ code. We'll use a classic example from the source material, a class that represents complex numbers. Numbers that have both a real part and an imaginary part.
So, without encapsulation, your main program could do something like this. It could just reach right into your complex number object, C1, and directly change its internal data, its real part. This is totally uncontrolled, it's unpredictable, and honestly, it's a recipe for disaster. It just breaks the whole idea of having a reliable object.
There's this perfect analogy for it. Letting other parts of your code have direct access is like having a super secure safe, but you just left it unlocked, sitting out in the middle of the street. What's the first thing you need to do? You've got to build some walls around it.
And in C++, these walls and doors have names. They're called access modifiers. We make our important data private, that's the wall. Only other functions inside that same class can even see it. Then we make our methods public, and that becomes our secure, controlled door to the outside world.
And here it is, the solution right in the code. See that private keyword? Now the data real and imag are protected. That line from before, c1.real equals 19, is now illegal. The compiler will literally stop you and say, nope, you can't do that. The only way to change the values now is by calling the public setComplex method. We've built our walls, and we control the only door.
Now, to make all this work as smoothly as it does, C++ gives us some really powerful tools. Let's just quickly look at two of the most essential ones you'll need for building good objects.
Okay, first up, references. The absolute easiest way to think about a reference is just as a nickname. So in this example, x and y are not two different variables. They are two different names pointing to the exact same chunk of memory. If you change y, you are simultaneously changing x.
And this is so critical for our methods. On the left, if you pass data normally, that's called by value, the function just gets a copy. The original is totally untouched. But on the right, if you pass by reference, you're giving the function that nickname to the original data. And that allows the function to actually modify the originals, which is exactly what a setter method needs to do. And then you have this cool feature called function overloading. This is actually a little taste of that third pillar, polymorphism. It lets you create multiple functions that have the exact same name, like sum, as long as they take different types of inputs. The compiler is smart enough to see if you gave it integers or decimals, and it calls the correct version of sum for you.
So let's just boil it all down. The key thing to remember is this. OOP is all about building reusable objects from class blueprints. Its first, most fundamental rule, encapsulation, is how we protect an object's important data by making it private, and then providing public methods so the outside world can interact with it safely. But here's the thing. Protecting an object is just step one. This question right here leads us straight to the next incredible pillar of OOP, inheritance. That's what lets us build new, specialized objects on top of old ones, making our code even more powerful and reusable. But that's a topic for another explainer. Thanks for watching.